Welcome to Stat Central's June seminar. The title of the seminar is Effect Size. P-values is not enough, measures of magnitude matter. This seminar follows on from last month's seminar that was exclusively on the idea of p-values itself. Before I go any further though, I'd like to make an acknowledgement of country. I'd like to acknowledge the traditional custodians of the land where UNSW's campuses stand. The Bedegal people at Kensington, the Gadigal people at Paddington, and the Ngunnawal people at Canberra. I would also like to pay my respects to the elders both past, present and emerging, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. As I mentioned before, this seminar is put on by Stat Central, which is the consulting unit, statistical consulting unit at UNSW. We provide statistical support to researchers throughout UNSW. That includes higher degree research students and staff, and we provide support in the areas of research design and analysis. If you'd like to find out more about the services we offer, and they're to a large extent free, go to our webpage and that'll give you a lot more detail. So today's seminar is, as I said before, about effect sizes and p-values, two things that go hand in hand in reporting of research results. The seminar is going to be given by Zhixin Liu, who is a statistical consultant with Stat Central. She has a lot of experience in study design and statistical modelling, particularly in medical research, including observational studies and clinical trials. At the end of the seminar, you'll be able to ask any questions that you want to about what Zhixin's spoken about. Can you please lodge your questions using the chat? That's probably the easiest way, since we've got about 125 people logged in at the moment. And I'll hand over to Zhixin.
Okay, thank you, Peter. So can everyone hear you clearly? So thank you for Peter for introduction, and thank you for everyone joining the seminar. And Peter have given a good connection between this seminar and the seminar given last month talking about p-value by our consultant Mark. So like we said, the p-value shouldn't be abundant. However, the p-value is not enough. The p-value is not enough, and the magnitude of the effect is more important. So we start our talk with a statement from Jacob Cohen. It says, the primary product of a research inquiry is one or more measures of effect size, not p-values. So let's start to look at what is the effect size, how we define it. So it's easier actually to define the effect size and the setting of comparing two conditions. So then the effect size is the magnitude of the difference between groups. And we have actually two sorts of effect size. One is the absolute effect size, and the other one is the standardized effect size, which is relative to the variability. So when we normally talk about effect size, actually we are referring to the standardized effect size. Let's look at the two plots below. So the left hand, they have the two, they indicate two groups. They have the same absolute effect size, which is the difference between the means of the two groups. But the left side, the distribution, the data is much more spread out, has more variability. And the right side, the two groups has like narrower distribution, so less variability. Then if we think about the difference between the mean and relative to the effect size, we can see they are quite different. And on the left side of the plot, actually the two groups, the distribution overlap a lot. While on the right side, the two groups separate quite clearly. So both absolute effect size and the standard effect size are both quite valuable for quantifying the intervention effect. And so if the original scale make like in the clinical setting make a lot of sense, so the absolute effect size is also very important to report. But in some behavior science or psychology, like those the scale, the instrument, the scale itself doesn't have much meaning. So then the standardized effect size is making more sense. Now let's start with a simplified example to demonstrate how we get the effect size. Why I call it a simplified example is I deliberately, if I with the example going on, I will show I deliberately put the standard deviation to be the same across the two groups. Okay. So now we look at, suppose we are comparing the blood lead level of the between the two groups of patients, and each group has 20 patients, n equal to 20, and group A has the mean of 22.7, and group B has the mean of 18.5, and they have the standard deviation both set at 7.5. Now, what's the absolute effect size? So it's simply just the difference between the two means, 22.7 and 18.5. So the difference is 4.2. And then we get the standardized effect size. That's the difference divided by relative to the standard deviation, 7.5. So we got the standard effect size 0.56. Okay, so the standardized effect size put different study settings on a similar scale, then they can be comparable. So now let's look at how the effect size is related to the significance testing. Continue on the example. Suppose we're gonna do the significance testing based on an independent two-sample t-test. Then how we get the t-value? So that is the difference between the two means divided by the standard error. Okay. So then what's the standard error? It is has two components. One is come from standard deviation, but also there is a number component, sample size component over here, highlighted in blue. Okay. So then one is easily to see that the t-value is actually the effect size, which is MA minus MB divided by the standard deviation, and then that's become the numerator of this t-value equation. And then the denominator is that sample size component. So when we do a little bit of calculation, so we have the t equal to the effect size 0.56. We get from the last slide. And then the sample size component, what we get is 0.32. So we get a t-value of 1.75 with a degree of freedom of 38. So we got a p-value 0.09. So that's where we see the effect size and the p-value connected. So now, how about we increase the sample size from 20 to 50? So then the t-value becomes 0.56. The effect size doesn't change, and then the sample size component becomes 0.2. So we have a larger t-value, 2.8. So when we increase the sample size, then the denominator, the value decrease. So we have a larger t-value. Then this time we got a p-value, smaller p-value, 0.006. So now we can see the significance test conflicts the effect size. That's the magnitude of the measure. And then the sample size, which indicates the precision. So next, we will see with the same effect size, we just vary around the sample size. We got minus 20 sample size. We got sort of insignificant result. And then if we increase the sample size to 50, we got a significant, statistical significant. So the statistical significant, next we're going to demonstrate it could be meaningless. So now we stay with the example, but we change the mean to get the difference between the mean smaller. So now the group A has a mean of 20.7, and group B, they have a mean level of the blood lead is 19.5. We keep the standard deviation the same. So now we have a smaller effect size, which is 1.2, the absolute, divided by the standard deviation 7.5, which is 0.16. If we stay with the sample size of 50 in each group, now we get a t-value 0.8, and the p-value is 0.43, insignificant. But how about when we increase the sample size into 500 for each group? We will see then the denominators associated with the sample size become very small, 0.06. And we got a t-value fairly large, 2.554. So okay, we got a significant p-value, 0.01. But the key thing is, so when we report, okay, we found a significant test, statistical significance, that really makes sense. So that depends on if that 1.2 difference or the 0.16 standardized effect size is clinically meaningful or not. So if we increase the sample size large enough for 5,000, we can detect whatever, probably 0.5 difference between the two groups, or 0.1. But that probably doesn't make any sense or make any difference clinically or in the field with the field knowledge. So that's why we say the pure statistical significance could be meaningless. And so here, then we have a plot which comes from a researcher reviewed around 100 randomized clinical trials. And then to look at the relation between the standardized target effect size, which is when you design your study. So based on this target effect size, you calculate your sample size. And then the y-axis indicates the standardized observed effect size. So the circle indicates 1 day after they conduct the trial, they report there is statistical significance, not statistical significance. And the cross indicates they found the reported statistical significance. So we will see if the circle, when the circles are across, so the circles normally stay at the lower part of the plot, which means the observed effect size is small, and then the target effect size could be large. So which means that the target effect size and calculate sample size not enough to detect the observed effect size. Okay, now we have looked at the relation between the effect size and the significance. Now let's move on to look at more closely about different index of the effect size. So we first start with look at the continuous outcome, and then we will look at the effect size for the dichotomous outcome. Hello, are we there? Okay. So the first we look at is the mean difference. We have with the prior example about the blood lead level, what we actually look at is the mean difference. So some of you might recognize what we put there is actually a very commonly used effect size called Cohen's-d. Okay, so that is the absolute difference between the two groups and relative to the standard deviation. And so actually depends on what kind of the standard deviation we use. They are slightly different index, the Cohen's-d, Huygens-g, and Glass delta. And normally, like I said, I simplify the example with the equal standard deviation, but in reality, the standard deviation will be different across the groups. But under the equal variance assumption, so we can get the pooled standard deviation. Depends on when we get the pooled standard deviation, what's the n used there. So the Huygens-g and the Cohen's-d are quite similar, but slightly different. And the Huygens suggested a correction when the sample size is small. So the Huygens-g actually is more well known for its correction. I didn't show the formula about the correction here, but it could be easily computed with the help of the software. And the rule of thumb is if your total sample size is less than 20, then we suggest use the Huygens correction. Otherwise, the effect size estimate will be upward, then higher than the true effect size. And for the Glass delta, then it's just simply use the control group standard deviation. The argument is some researchers believe the experimental intervention arm will make the variation different. So the control group can reflect the true population, the standard deviation. And the next, another family about the effect size is called the variance explained. So that's not based on the mean difference, it's based on the proportion of the variance explained in the dependent variable. And the commonly used ones are the Pearson's R, the correlation coefficient, and the R square is basically the proportion of the variation explained. And also under the ANOVA setting is the Cohen's F, that's the ratio of the, again, the standard deviation from the between group variation and the total variation. And under the multiple regression setting, then it's about the eta square and the partial eta square, also the Cohen's F square is commonly used. So then for the dichotomous outcome, so which is when we have a binary outcome. So for the blood lead example, if we have a cutoff, cut the blood lead level to high and low, and then compare across the two groups, then we will have the 2x2 contiguity table. So then for the effect size, we can, by looking at the risk difference, that's the difference between the two proportions. Say the proportion of a high blood lead between group A and group B. And also we can look at the ratio, like that is the proportion in group A and compared to the proportion in group B. And the other one is that's relative risk, and the other one is the odds ratio. And the odds ratio comparing the odds for each group. The odds is the proportion, the case, the event, and over the number of non-event. Okay. So each of these indicators has advantage or disadvantage. And for the odds ratio is more commonly used when we have because the logistic regression model is the most commonly used model for modeling the binary outcome. And the next one, the Cohen's H and the Cohen's W, these two are less commonly used. But the Cohen's H is sometimes useful, particularly when we want to look at the sample size, but we don't have good prior knowledge about the proportion from each group. So the H comes from the doing the arc-sin transformation of the square root of the proportions. So the point for doing this is, with this transformation, the equal difference and has the equal power. But if we just look at the risk difference, so from 0.1 to 0.3, the difference is 0.2, and it's different from we have 0.5 to 0.7, the 0.2. But with the arc-sin transformation, we can have a kind of the equal the difference, the H, to guide us for the power analysis. And the Cohen's W is based on the chi-square test, and it's basically sum up the difference of the null hypothesis, the proportion, and the alternative hypothesis proportion for each cell. So far, what we talked about, the effect size are commonly used, but also they assume the normality and the homogeneity, the normality for distribution and homogeneity for the variance. And there are other estimators. So when these assumptions failed, so a sample size is small and the normality and the homogeneity couldn't meet. And so researchers proposed some alternative effect size index that's based on some robust non-parametric statistics. The commonly used one is called the Glyphs delta. So that's already developed for ordinal data. So that's relative to a non-parametric version of the t-test, the Mann-Whitney test. And the other one proposed is called Weigha-Delaney A statistics. And that is a non-parametric estimator for index called common language effect size. So the common language effect size is a kind of effect size proposed by the researchers aiming at to communicate on an equal platform to non-statisticians. So this is basically a probability of superiority. So that is the probability if you randomly pick up a score from group A, and that probability is higher than the score you randomly pick up from group B. Okay. So one we talk about quite many effect size index. So there particularly Cohen proposed some cutoff, then the threshold to make the some like categorize the effect size into small, medium, and large. And that's with the purpose to ease the interpretation. So we will roughly know we are aiming to detect a small effect size or a medium effect size. So that is sometimes quite useful for the sample size estimation, particularly when the researcher doesn't have two historical data or pilot data or rich prior publication. You can find the information. But the point is we do encourage people, if you have this prior data information, we encourage we have a more rigorous effect size estimation rather than just simply based on a small or medium, this kind of rough indication. But this table does summarize with different cutoff for different effect size indicators. The effect size itself is reflects the magnitude of the effect. It's very useful, and it would be even more useful if we can come with the precision about the effect size, which is we give the margin, estimate the margin for the error of the effect size, and provide a confidence interval. So here I just put the example for the Cohen state, but there are other margin for error for like Cohen's F square all available. We don't have to compute ourselves most of the time, and we can some software can help us. So for this particular one, we have then the margin for error for the Cohen state have this formula here, and then we again apply the point estimate of the effect size plus or minus that Z 0.025 significance level and times that margin of error. So for our blood lead level comparison, we have the effect size of 0.56 and with the sample size of 50 for each group. And we have the margin of error estimated at 0.2. So then we have the confidence, 95% confidence interval for this effect size is range from 0.17 to 0.95. So that gave an indication of how precise your observed effect size is. So for the effect size calculation, the tools is not as readily available as the significance test, but we do have some R package can help us do some common effect size index. So there is a package called compute.es. So from this package, we would be able to have the estimate of Cohen's D, Huygens A, Huygens G, and the non-parametric one, the Cliff delta, and also for the detromatous ones like the odds ratio, and also the correlation one R. And this is quite useful for this package because it can convert the test statistics, help you to convert that into the effect size index. And the other package, they called EF size, also can mainly do the mean difference effect size index, non-parametric and parametric. And it mainly computes that index from your original data. Okay, so we have talked about effect size, and so where we use it. So definitely we have been talking about the effect size is so useful and so important to to include in our result and findings to demonstrate the evidence of our study, our finding. And in the meanwhile, we can imagine, so when we publish our effect size, then either ourselves or other researchers can follow and can use the information to borrow the effect size and then to incorporate into their sample size estimation for their future studies. Another useful part, and some of you probably have been using, is to use effect size in the systematic review in that research synthesis scope. So that is where then we can cross-compare effect size with different studies and also combine and analyze the effect size through the meta-analysis. When we conduct meta-analysis or systematic review, it's quite a common the problem or challenge is, so different studies, they report different effect size. So that could limit our ability to include them. So here we have, we can try to translate between different effect size. So this table is come from a publication by Fries and Richler that could help the conversion between different effect size to help our meta-analysis. Okay, so let's wrap up this talk with a statement from class. So the statistical significance is the least interesting about the results. You should describe the results in terms of the measures of magnitude, not just does a treatment affect people, but how much does it affect them. So the magnitude of the effect. And reporting the effect size facilitates the interpretation of the substantive significance of our result. So like we talked about, statistical significance could be meaningless because when we have a huge, tremendous sample size, you always can detect a very minimum or even ignorable effect size. But so the true effect size we found, and that is the substantive significance we trying to deliver to the readers. And in terms of what to report for the effect size, so like we said, so the effect size will be used by other researchers for meta-analysis or for further research. So more detail will be better. And at least we should indicate what effect size is cohort or it is the cohort F square whatsoever we used, and how it is calculated. So even like for the mean difference, what kind of standard deviation is pooled standard deviation or is the control arm standard deviation we used? And it would be the best to report also the precision of the effect size, which indicated by the confidence interval, at least maybe for your primary outcome. So here then is a sample description about the how to report the effect size together with the significance testing. So for the blood lead level example, we can state, so a sensitivity test indicate the blood lead level was significantly higher for group A with the mean 20 22.7 and standard deviation of 7.5, and the group size is 50. So that's a detailed descriptive information about our data. And then the mean standard deviation and N for group B. So the difference is 4.2, that's the absolute effect size, and the confidence interval is 1.27 to 7.14. And the test statistic is 2.8, p-value 0.06, and then the effect size cohort B then is 0.56. So that is what the effect size index we use. And also the confidence interval for the cohort D is 0.17 to 0.95. So here is some reference for the effect size, different type of effect size, and where and when to use them, and that and also a couple of links, that's good resources to guide us to use the effect size. Okay, so thank you for your attention, and the link below is our State Central website for browse some useful information, and also for booking consultation with us. Thank you.
Great, thanks very much, Zhixin, for a really interesting and practical and useful seminar. And we've got some questions ready. The first one is from Jingyi, and the question is it okay to define a significant effect based on whether the mean plus or minus a 95% confidence interval crosses 0, or should there be a formal test, like a t-test?
That's actually, if we talk about the confidence interval for the effect size, or we are talking about confidence interval for the absolute difference. If the absolute difference, then the confidence interval and the t-test, they actually are quite kind of like equivalent. So you cross 0, which indicates insignificant result, but that gives us a magnitude about what you found and the precision. And then for the effect size and the confidence interval, again, so it reflects the significance, but the focus is if the effect size is not if the effect size is away from 0 or not. Is the effect size, how big the effect size is. So comparing to 0 become not that important. That's also the point, like the p-value is not that important.
Great, thanks, Zhixin. Another question is from Rani. Does bootstrapping produce larger effect sizes?
So I don't think there is definite answer, and the bootstrapping could have so the effect size is about standard deviation, I presume. The bootstrapping might give a larger or smaller standard deviation compared to the traditional way we got standard deviation. So I would say that's not necessarily.
Okay, great. Another question, this time from one of the Marks tuned in. G-Power asks for an effect size F. Is this Cohen's F? And how can you calculate F from data?
Yes, that's a good question. So if under the ANOVA setting, I would say that F is indicate that the core has F. So for some publication, if you are looking at the prior literature, it could be reported. Or if because the F is the ratio is the of the between group variation and the total variation, the sum the sum square error. So it if it can report it in the literature, they report the result in detail about this separation of this variation between group within group and the total. Then we can get it, calculate ourselves.
It's coming. We've still got some more though. If the standard deviation for different groups is different,
yeah.
How do you calculate the effect?
Yeah, that's a very practical question. So the standard deviation for the groups, normally they are different. So it depends on how different they are. So if to the extent we still can assume that equal variance assumption, so the homogeneity assumption, so that's where the pooled standard deviation is used. But however, if there are dramatic difference between the groups in terms of standard deviation, so which is fell into the gray, then the homogeneity assumption failed, or this is the equal variance failed. So that's where we introduce that robust statistics, non-parametric statistics, like the Cliff's delta could be used for that.
Zhixin, we haven't got any more questions yet, so we give people a couple more minutes to think of a last question.
Yep.
Zhixin, maybe I've got a question. Can you tell us a bit about what some of the more commonly used statistical packages can do in calculating effect sizes? Because you said during the talk that some of the tools were not really widely available in software.
You're right. They are not as readily available as those statistical testing tools. So my feeling is the effect size. So given the greatest amount of p-value over the years and the increasing, and the effect size is getting more and more attention, and the recognition of this importance, I think the more practical tools in R or in other software like SPS and SAS will become more available. So I think, I'm not sure if SPSS I think has bit function for that, but maybe still I need a bit hand calculation for most of the index.
Great, thank you. Oh, we've got another question. If the confidence interval includes 0 in a risk difference, what do you do in that case?
So the risk difference, right? So that if we are that's about, I think we are talking about again the significance testing, isn't it? So if we care about if that's away from 0 or not, the 0 means no risk difference. The two proportions are equal. So that kind of like a statistical testing. If cross 0, which means we say it's insufficient. But then we can report the effect size in terms of like, so even though it's cross 0, but how far away, so the lower end and the upper end boundary of the interval, and the point estimate how far away from 0. So that is the magnitude of that. So then if a cross 0, maybe simply because you don't have, you are powered to detect the effect size you tend to detect. So it's like the blood lead example, when we have 20 in each group. So the common interval will cross 0 of difference. But if we increase the n to 50, so you got p-value 0.06, which means the confidence interval will away from the 0. But the point estimate is the same.
Great, thanks. And another question, this time from Darwin.
Okay.
Darwin's asking about GLMs and wants to know what you do about effect sizes for GLMs, and also what about in non-parametric tests is the second part of that question.
Yeah, I think that's a good question. So when it's come to generalized linear model, it will I think become more complicated, and also that's something I didn't mention in the talk. Like even one is multi-level or it's repeated mixture, so things all getting more complicated. I would say the regression coefficient we report the beta, the coefficient when we do the GLM and the confidence interval visit would be a sort of indicator for the effect size. But the thing is not like as clear as Cole has did those traditional index, like we have small, medium, or large. We might not have that clear definition. And for the non-parametric, I think if we can't connect the effect size in the conventional effect size we talked about, or the assumption related. So one way we can always do is to report the absolute difference. And the other one is use what we talked about, some non-parametric indicator like Cliff's delta or the A statistic to use those indicators. But I think that the trend is, I think there can be more effect size research methodologists working on it. So it's become it will become more available of these indicators.
Great. We've got one question. Maybe this can be the last one since we're nearly up to time. It's from Claudia, and she's asking if you have wide confidence intervals, can you draw conclusions about the effect size?
Yes. So I guess for the effect size, it's what we honestly report, what we found. So it's perhaps not at a kind of a conclusion, but like I put in a sample statement. So we indicate that we have this is the absolute difference, and this is the confidence interval we can see is very wide, and we perhaps a p-value which is also quite big, 0.2. But we have the effect size estimate here, like is a median, say 0.5. That's not a very ignorable effect size. It's kind of like it's clinical meaningful. But then we have, in your case, I would think then the confidence interval for your effect size is quite wide, which indicates the precision is not very good for this study. Perhaps you are not have enough sample size. So that is honestly your report, what you found. You have that quite meaningful effect size, but it's not have a good precision in your study. So maybe that works well for future study, to have a large scale study for other researchers to do some further work on it, or meta-analysis to include your study can be included in the meta-analysis and to see if that's a genuine effect or it is just an effect like randomly happen but not real.
Okay, well no more questions have come in, so maybe we'll finish up there. Thanks very much, Zhixin, for a great talk. It was really interesting and really practical. And thanks everybody for all those great questions too that really filled out the discussion. Next month, we'll have another seminar at the regular time, second Thursday of the month at 2:30, so that's the 9th of July. And if you're into long-term planning, Stat Central is going to run a series of its short courses again in August. So have a look on our webpage. They're all R-based. Introduction to R, Intro Stats, and Introduction to Regression Modeling in R. So hope to see you in... Bye, everyone.